You are listening to the Solid Blueprint, crafting flexible and maintainable software design. Subscribe to keep up to date on our latest audiobooks. The Solid Blueprint, crafting flexible and maintainable software design. Chapter 1, The Foundation of Good Design. Imagine stepping into a newly built house. It looks beautiful from the outside, the paint is fresh, and all the fixtures gleam. But a few weeks later, cracks appear in the walls, the plumbing leaks without warning, and the electrical outlets spark when you plug something in. What went wrong? The house might have looked good superficially, but its underlying design was flawed. It was built without a sturdy foundation, without proper planning, and without adherence to proven engineering principles. Software is much the same. We write code, build applications, and deliver features. On the surface, a program might seem to work perfectly fine. It solves the immediate problem and everyone is happy. But as time goes on, new features are requested, bugs need fixing, and the initial team moves on. That's when the cracks begin to show. What once seemed like a simple change can ripple through the entire system, causing unexpected failures elsewhere. Tracking down a bug becomes akin to finding a needle in a haystack, made worse by tangled relationships between different parts of the code. Adding a new feature feels like forcing a square peg into a round hole, requiring you to dismantle half the existing structure. This phenomenon is what software developers call technical debt, the hidden cost that accrues when code is poorly designed and rushed into production. The invisible cost of bad design. Technical debt isn't just an abstract concept. It has real, tangible costs. It slows down development, frustrates engineers, increases the likelihood of errors, and ultimately impacts the bottom line of businesses. Projects fall behind schedule, budgets balloon, and innovation grinding to a halt. Teams spend more time maintaining existing code than building new features. It's like owning a classic car that spends more time in the repair shop than on the road. This book is about avoiding that fate. It's about learning to build software not just for today, but for tomorrow. It's about creating systems that are resilient, adaptable, and a joy to work with, rather than a source of constant headaches. What is software design anyway? Before we dive deep, let's clarify what software design entails. It's not just about drawing diagrams or choosing programming languages. In essence, software design is the process of defining the architecture, components, interfaces, and other characteristics of a system or component. It's about deciding how the different parts of your program will interact, what responsibilities each part will have, and how they will evolve over time. Good design is about making choices that prioritize clarity, flexibility, and maintainability. It's about thinking ahead, anticipating change, and structuring your code in a way that minimizes future pain. The context. Object-oriented programming, OOP. The principles we will explore in this book are primarily rooted in object-oriented programming, OOP. If you've worked with languages like Java, C#, Python, or C++, you're likely already familiar with some of its core concepts. OOP provides a powerful paradigm for structuring code, allowing us to model real-world entities and their interactions. At its heart, OOP revolves around objects, which are instances of classes. These classes group together both data attributes and behavior methods into self-contained units. Key concepts like encapsulation, hiding internal details, inheritance, creating hierarchies of classes, and polymorphism, objects taking on many forms, are fundamental tools that OOP developers use. While this book doesn't assume you're an OOP expert, we will quickly revisit these foundational concepts in Chapter 2 to ensure we're all on the same page. Understanding these building blocks is essential, as the design principles we're about to discuss leverage them to achieve their goals. Introducing Solid, your design compass. In the world of software engineering, there are sets of tried and true guidelines that seasoned developers use to navigate the complexities of system design. Among the most influential and widely adopted are the Solid principles. Coined by Robert C. Martin, affectionately known as Uncle Bob, these 5 principles serve as a powerful compass for object-oriented design. Each letter in Solid stands for a distinct principle. S. Single responsibility principle. A class should have only one reason to change. O. Open-closed principle. Software entities, classes, modules, functions, etc. should be open for extension but closed for modification. Liskov Substitution principle. Objects in a program should be replaceable with instances of their subtypes without altering the correctness of that program. Interface segregation principle. Clients should not be forced to depend on interfaces they do not use. Dependency Inversion principle. High-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. These aren't rigid rules to be followed blindly, but rather guiding principles like a craftsman's wisdom passed down through generations. They are designed to help you create software that is flexible, easily adaptable to new requirements without massive overhauls, maintainable, simple to fix bugs and understand how the system works, reusable. Components can be used in different contexts. Testable, individual parts can be easily verified in isolation. Over the next few chapters, we will dedicate a full exploration to each of these powerful principles, breaking them down into easily digestible concepts, illustrated with relatable examples and practical scenarios. Whether you're just starting your journey in software development or you're a seasoned professional looking to refine your craft, mastering Solid will undoubtedly equip you with the tools to build software that stands the test of time. Let's begin by ensuring we have a shared understanding of the core concepts of object-oriented programming. Chapter 2, Setting the Stage, Core OOP Concepts Revisited. Before we plunge into the specifics of each solid principle, it's essential that we establish a common vocabulary and understanding of the fundamental building blocks of object-oriented programming, OOP. The solid principles are deeply intertwined with OOP, leveraging its features to achieve their design goals. If you're already very familiar with these terms, consider this a quick refresher. If they're new, don't worry. We'll explain them simply and clearly. 1. Objects and classes, the building blocks. Imagine you're building a car. You don't start by carving out a piece of metal for every single car you produce. Instead, you design a blueprint or a schematic for a car. This blueprint defines what every car of that model will look like, what parts it will have: engine, wheels, seats, and what it can do: drive, brake, turn. In OOP, that blueprint is a class. A class is a template or a definition for creating objects. It describes the data, properties, or attributes, and the behaviors, methods, or functions that objects of that type will possess. Once you have the blueprint, you can build many actual cars from it. Each individual car, built according to the blueprint, is an object. An object is an instance of a class. Each object has its own unique set of data, e.g., this car is red, that car is blue, but shares the same potential behaviors as defined by its class. Example, class. Car defines that a car has a color, make, model, and can start, stop, accelerate. Object 1, my red car, an instance of car, color, red, make, Honda model Civic. Object 2, your blue car, an instance of car, color, blue, make, Ford model Focus. 2. Encapsulation, protecting your data. Think about your smartphone. You use it every day, but you don't need to know how the processor works, how the memory stores data, or how the screen displays images. You simply interact with its external buttons and touchscreen commands. The intricate internal workings are hidden away. This concept is encapsulation. In OOP, it means bundling data, attributes, and the methods, behaviors that operate on that data into a single unit, the object. More importantly, it involves hiding the internal state and implementation details of an object from the outside world, exposing only what is necessary through a well-defined interface. Why is this important? Reduces complexity. Users of the object don't need to know the inner workings, they just need to know what it does. Increases maintainability. If you change the internal implementation of an object, as long as its external interface remains the same, other parts of the system that interact with it won't be affected. This prevents changes from rippling unnecessarily throughout the codebase. Prevents misuse. By hiding certain data or methods, you can prevent other parts of the program from directly manipulating the internal state in ways that could lead to errors. Example, a bank account class might have a balance attribute. Instead of allowing other parts of the program to directly change balance, you provide deposit and withdraw methods. These methods encapsulate the logic for handling balance changes, ensuring that all operations maintain the bank's rules, e.g., preventing negative balances. 3. Inheritance. Building on what exists. Imagine you have a general blueprint for a vehicle. This blueprint defines common properties like speed and common actions like drive. Now, you want to create blueprints for more specific types of vehicles, like a car and a motorcycle. Instead of starting from scratch for each, you can say, a car is a vehicle and a motorcycle is a vehicle. This is inheritance. It's a mechanism where a new class, car or motorcycle, called the subclass or derived class, can inherit properties and behaviors from an existing class, vehicle, called the superclass, base class, or parent class. Why is this important? Code reusability. Common properties and methods defined in the superclass don't need to be rewritten in every subclass. Establishes relationships. It models a relationships in the real world, e.g., a dog is an animal, a sedan is a car. Extensibility. You can extend the functionality of a base class without modifying it, which directly ties into the open-closed principle we'll discuss later. Example, vehicle superclass has start engine, stop engine, accelerate. Car subclass inherits from vehicle and adds specific properties like number of doors and methods like turn on wipers. Motorcycle subclass inherits from vehicle and adds properties like has sidecar and methods like lean into turn. 4. Polymorphism, many forms, one interface. The word polymorphism comes from Greek, meaning many forms. In OOP, it means that objects of different classes can be treated as objects of a common type, or that a single interface can be used to represent different underlying forms. Consider a universal remote control. You can use it to turn on your TV, your DVD player, or your sound system. The remote uses the same power on button or volume up button, even though the internal mechanisms for each device are completely different. The remote interacts with each device through a common interface, the buttons, and each device responds to those commands in its own way. In software, polymorphism allows you to write code that interacts with objects at a higher, more abstract level, without needing to know their specific underlying types. Why is this important? Flexibility. You can add new types of objects without having to change existing code that uses the common interface. Simplicity. Code becomes cleaner and easier to understand because it focuses on what an object does, rather than how it does it for every specific type. Extensibility. New functionality can be seamlessly integrated. Example, shape abstract base class or interface defines a common method calculate area. Circle subclass implements calculate area based on its radius. Rectangle subclass implements calculate area based on its length and width. You could then have a list of shape objects, some are circles, some are rectangles, and call calculate area on each without caring about its specific type. Each object would correctly calculate its own area. 5. The importance of abstraction. Closely related to encapsulation and polymorphism is abstraction. While encapsulation hides complexity, abstraction manages it by focusing on the essential characteristics of an object while ignoring irrelevant details. It's about providing a clear, simplified view of something complex. Think of driving a car. You interact with the steering wheel, pedals, and gear stick. You accelerate, brake, turn. You don't need to understand the combustion process of the engine or the precise mechanics of the transmission. The abstraction of driving allows you to operate the vehicle effectively. In OOP, abstraction often involves using abstract classes and interfaces. An abstract class is like a partial blueprint. It can define some common behaviors, but leaves other behaviors unspecified abstract methods to be implemented by its concrete subclasses. You can't create an object directly from an abstract class. An interface is even more abstract. It's like a contract or a pure blueprint that defines a set of methods that a class must implement if it claims to adhere to that interface. It specifies what a class can do, but not how. Why is this important? Focus on behavior. Encourages designing systems by focusing on the responsibilities and behaviors of components, rather than their concrete implementations. Decoupling reduces dependencies between different parts of the system. If components depend on abstractions, interfaces, rather than concrete implementations, It's easier to swap out one implementation for another without affecting the dependent component. Flexibility provides a framework for building highly flexible and extensible systems. Example, iPayable interface defines a method getAmountDue. Invoice class implements iPayable, calculating amount due for goods services. Employee class implements iPayable, calculating salary amount due. Because both invoice and employee implement iPayable, you can interact with them generically through the iPayable interface to get their respective amounts due, without needing to know if you're dealing with an invoice or an employee. This is pure abstraction in action. With these fundamental OOP concepts in mind, you now have the necessary foundation to understand and appreciate the power of the solid principles. Each solid principle we explore will build upon these ideas, showing you how to apply them to create robust, flexible, and maintainable software designs. Let's begin our journey with the first principle, the Single Responsibility Principle. Chapter 3, the S in Solid, Single Responsibility Principle, SRP. Our journey into the solid principles begins with the S, the Single Responsibility Principle, SRP. This principle is foundational, often considered the cornerstone of good object-oriented design. While its name might sound straightforward, its true meaning often gets misinterpreted. The principle: a class should have only one reason to change. Robert C. Martin, Uncle Bob. At first glance, you might think this means a class should only do one thing or have only one method. But that's not quite right. The key phrase here is reason to change. A class can perform multiple functions, as long as those functions are all related to its single responsibility, and if a change in those functions stems from the same cause. The reason to change analogy. Think about a traditional Swiss Army knife. It's an ingenious tool that packs a knife, screwdriver, can opener, bottle opener, and more into a single compact unit. It fulfills a single purpose, being a versatile, portable multi-tool. However, if your specific task requires a heavy-duty screwdriver, a sharp chef's knife, or a robust wood saw, the Swiss Army knife, while capable, isn't the best tool for the job. Why? Because if you need a better screwdriver, you have to buy a whole new Swiss Army knife, even if you like its current knife blade. The screwdriver's reason to change is bundled with the knife's reason to change. Now consider a dedicated set of tools: a hammer, a screwdriver set, and a wrench set. Each tool has a single, clear responsibility. If you need a different size screwdriver, you only change the screwdriver set, not your hammer or wrench. Each tool has only one reason to change, improvements or changes specific to its function. In software, a class with one reason to change is like a dedicated tool. If a part of your system changes for one reason, you should ideally only have to modify that one responsible piece of code. If a change for a different reason forces you to modify the same piece of code, then that piece of code likely has more than one responsibility. Manager, chef, and waiter, a real-world analogy. Imagine a restaurant. You might have several roles. The chef, their responsibility is to prepare food. If a new dish is added to the menu or a preparation method changes, the chef is the one who needs to adapt. That's their reason to change. The waiter, their responsibility is to serve customers. If new seating arrangements are introduced or the ordering process changes, the waiter adapts. That's their reason to change. The manager, their responsibility is to manage operations. If supplier contracts change or staff schedules need adjusting, the manager adapts. That's their reason to change. What if one person tried to be the chef, the waiter, and the manager all at once? They would be constantly pulled in different directions. A change in the menu, chef's task, might clash with taking new orders, waiter's task, or a staff issue, manager's task, might delay food preparation. This jack-of-all-trades approach, while sometimes necessary in tiny startups, quickly becomes unsustainable and error-prone as complexity grows. SRP in software. Separating concerns. In software, SRP encourages us to assign distinct, well-defined responsibilities to individual classes or modules. Common examples of responsibilities include business logic, the core rules and computations of your application; data storage retrieval, how data is saved to and loaded from a database, file, or external service; user interface, UI, presentation, how data is displayed to the user, and how user input is handled. Reporting, generating specific formatted reports. Logging, recording application events. Let's consider a classic software example, a user class. Problem: SRP violation. Imagine a user class that looks something like this. It stores user information such as name, email, and password hash. It contains methods to save the user to a database and load the user from a database. It also has a method to send a welcome email after user registration, and perhaps even a method to display the user profile on a web page. This single user class has multiple reasons to change. If the user data structure changes, e.g., adding a new field like phone number. If the database technology changes, e.g., moving from a SQL database to a NoSQL database. If the welcome email content or sending mechanism changes, e.g., switching email providers. If the way the user profile is displayed on the web page changes, e.g., moving from HTML rendering to a JSON API. Each of these changes impacts the same user class. A bug fix in the email sending logic could inadvertently affect the database saving logic. This intertwining makes the code harder to understand, test, and maintain. Solution: SRP compliant. Applying the single responsibility principle would mean separating these concerns into distinct classes, each with its own single reason to change. User class. Responsible purely for holding user data, name, email, password hash. Its reason to change is solely if the structure of user data changes. User repository class or user data store. Responsible for managing the persistence of user data, saving to loading from the database. Its reason to change is if the data storage mechanism changes. Email service class or welcome email sender. Responsible for sending emails. Its reason to change is if the email sending logic or content changes. User profile presenter class or user web renderer. Responsible for preparing and displaying user profile data for the user interface. Its reason to change is if the user interface rendering logic changes. Now, if a change to the database structure is required, you only modify user repository. If the welcome email needs a new template, you only touch email service. This separation makes the system much more modular, understandable, and resilient to change. Benefits of SRP: increased maintainability. Changes are localized. When a requirement changes, you know exactly where to go, minimizing the risk of introducing bugs elsewhere. Improved testability. Each class is smaller and has a specific purpose, making it easier to write focused unit tests for it in isolation. Enhanced reusability. A class responsible for only one thing is more likely to be reusable in different contexts. An email service can be used to send all kinds of emails, not just welcome emails tied to user registration. Better readability and understanding. Smaller, focused classes are easier for developers to read, understand, and reason about. Common pitfalls. Oversegmentation. Don't go overboard and create a new class for every single method. The reason to change is the guiding principle. If multiple methods change for the same reason, they likely belong together. Misinterpreting responsibility. It's not about one function, but one concept of responsibility. Ignoring SRP early on. While it might seem like overkill for small applications, neglecting SRP early on can lead to God objects or monoliths that are incredibly difficult to refactor later. An anecdote: the do-everything class catastrophe. I once worked on a legacy system where there was a single, gigantic class called order processor. This class was thousands of lines long. It handled validating order items, calculating taxes, applying discounts, processing credit card payments, sending order confirmation emails, updating inventory, and even generating an invoice PDF. The first time we had a bug with credit card processing, we fixed it, but then found that the inventory numbers were off. Later, when we updated the tax calculation rules, the invoice PDF started showing incorrect formatting. Each reason to change, payment, inventory, taxes, emails, PDF generation, was intertwined within this single order processor class. Debugging became a nightmare of stepping through unrelated logic. Every change was terrifying because of the high risk of breaking something else. Refactoring this beast using SRP involved breaking it down into order validator, payment processor, inventory service, email confirmation sender, and invoice generator classes. It was a painstaking process, but the immediate benefits were clear. Changes became localized, testing became simpler, and the fear of unintended side effects diminished significantly. It wasn't just about cleaning up the code. It was about regaining control over the system's evolution. The single responsibility principle is subtle but powerful. It encourages us to think about the underlying forces that drive change in our systems and to isolate those forces into distinct, manageable units. Mastering SRP provides a strong foundation for the other solid principles, many of which build upon its wisdom. Next, we'll explore the open-closed principle, which leverages well-defined responsibilities to make our software truly extensible. Chapter 4, the O in Solid, Open-Closed Principle, OCP. Having understood the importance of the single responsibility principle, we now move to the O in Solid, the Open-Closed Principle, OCP. This principle is arguably one of the most critical for building flexible and adaptable software systems. The principle, software entities, classes, modules, functions, etc., should be open for extension, but closed for modification. Bertrand Meyer, original formulation, Robert C. Martin applied to OOP. Let's break down this seemingly paradoxical statement. Open for extension. This means that the behavior of a module can be extended or altered to meet new requirements. You should be able to add new functionality without changing the existing working code. Closed for modification. This means that once a module has been developed and tested, its source code should not be changed to add new functionality. You shouldn't have to rewrite or alter the proven, stable code. The goal of OCP is to minimize the impact of changes. When you need to add a new feature, you ideally want to write new code that plugs into the existing system, rather than changing tried-and-true components. The appliance analogy. Think about a standard electrical wall outlet in your home. This outlet is designed to deliver power. It is closed for modification. You, as the user, don't typically open up the wall, fiddle with the wiring, or change the voltage of the outlet just because you bought a new appliance. The outlet's internal mechanism is fixed and reliable. It is open for extension. When you buy a new device, a phone charger, a lamp, a toaster, you can simply plug it into the existing outlet. You extend the functionality of your home's electrical system by adding new devices without changing the outlet itself. The new device relies on the interface of the outlet, the prongs, and the voltage. Now imagine a less OCP-compliant system. What if every time you bought a new type of appliance, you had to rewire your wall outlets specifically for that appliance? Or if your toaster needed a completely different type of power supply than your lamp? That would be chaos, expensive, and fragile. Your electrical system would be incredibly difficult to maintain and extend. This highlights the essence of OCP. Use abstractions, like the outlet standard interface, to shield callers from concrete implementations, allowing new implementations to be added without altering the established structure. OCP in software. Using abstractions and polymorphism for flexibility. In software, OCP is typically achieved through the strategic use of abstraction interfaces or abstract classes and polymorphism. Instead of relying on concrete implementations directly, modules depend on stable abstractions. New functionality is then added by creating new concrete classes that implement these abstractions, plugging them into the system without touching existing code. Let's consider a common scenario, calculating the shipping cost for various types of products. Problem: OCP violation. Imagine a shipping cost calculator class designed to determine shipping fees. Initially, you might only ship books. Class shipping cost calculator, method calculate shipping item. If item is book, return item weight 0.50. LC, return 0, default or error. Later, you start selling electronics. You modify the calculate shipping method. Class shipping cost calculator, method calculate shipping item. If item is book, return item weight 0.50. Else if item is electronics, return item weight 0.75 plus item value 0.01, added new logic. LC, return 0. This violates OCP. Every time a new product category or shipping rule emerges, e.g., clothing, oversized items, international shipping, you have to go back into the shipping cost calculator class and modify its existing calculate shipping method by adding another else if condition. This means the class grows larger and more complex. It becomes a single point of modification, increasing the risk of introducing bugs. You have to retest the entire calculate shipping method, not just the new logic. Solution: OCP compliant. To apply OCP, we introduce an abstraction that represents the concept of calculating shipping for an item. Define an interface or abstract class. Let's create an abstract concept called iShipping strategy. This defines a contract. Any class that implements iShipping strategy must provide a method to calculate item. Interface iShipping strategy, method calculate item. Returns decimal. Create concrete implementations for each strategy. Now, for each specific shipping rule or item type, we create a new class that implements iShipping strategy. Class bookShipping strategy implements iShipping strategy. Method calculate item. Return item weight 0.50. Class electronics shipping strategy implements iShipping strategy. Method calculate item. Return item weight 0.75 plus item value 0.01. New class, new logic. Class international shipping strategy implements iShipping strategy. Method calculate item. Return item weight 1.20 plus item customs fee. Another new class. Refactor the shipping cost calculator. The shipping cost calculator itself no longer needs to know the specific details of how shipping is calculated. It just needs an iShipping strategy. Class shipping cost calculator, private shipping strategy, iShipping strategy. Constructor strategy, iShipping strategy. This shipping strategy equals strategy. Method get cost item. Return this shipping strategy calculate item. Now, if you introduce a new oversized item shipping strategy, you simply create a new class, oversized item shipping strategy, that implements iShipping strategy. Ready. No modifications to shipping cost calculator are required. It is closed for modification concerning shipping rules, but open for extension by adding new shipping strategies. When you want to calculate shipping for a book, you give the calculator a book shipping strategy. For electronics, you give it an electronics shipping strategy, and so on. This dynamic assignment is where polymorphism shines, allowing shipping strategy calculate item to behave differently depending on the specific strategy object it holds. Benefits of OCP: reduced risk of bugs. When you extend functionality by adding new code rather than modifying existing, stable code, you reduce the chances of introducing regressions, bugs in previously working features. Increased code stability. Core, proven parts of your system remain untouched, making them more reliable. Improved maintainability. Locating and understanding specific functionalities becomes easier as new functionality is encapsulated in new, focused classes. Enhanced testability. New strategies can be tested independently without impacting the shipping cost calculator itself, which is simpler and more stable. Greater flexibility. Allows your system to adapt to unforeseen future requirements. Common pitfalls: over-engineering. Don't apply OCP everywhere, especially for features that genuinely have a single, fixed logic. Sometimes, a simple if-else is perfectly fine if the logic is unlikely to change or extend in various ways. Applying OCP unnecessarily can lead to excessive abstractions and complexity. Predicting the unpredictable. While OCP encourages foresight, it's impossible to predict every future extension. Focus on areas that are known to change or extend polymorphically. Incorrect abstraction. If your abstraction interface isn't stable or doesn't truly capture the concept that needs extension, you might find yourself needing to modify the abstraction itself, which violates OCP. An anecdote: the payment gateway saga. In a previous role, we had an e-commerce platform that initially integrated with only one payment gateway. All the payment processing logic was hard-coded directly into an order service class. As the business expanded internationally, we needed to support multiple payment gateways, each with its own quirks and API. Initially, developers crammed if-else if blocks into order service. If gateway is PayPal, call PayPal API, else if gateway is Stripe, call Stripe API. This quickly became unmanageable. Adding a new gateway meant days of work, not just integrating the new API, but carefully navigating the existing, brittle order service logic to avoid breaking the old gateways. The order service was constantly modified. The solution, though a significant refactor, was to implement OCP. We created an iPayment gateway interface defining methods like process payment and refund. Then, we made concrete classes like PayPal Gateway, Stripe Gateway, etc., each implementing this interface. The order service was then refactored to depend on iPayment gateway abstraction, receiving the specific gateway instance it needed at runtime. Suddenly, adding a new payment gateway became a trivial task. Write a new gateway class that implements iPayment gateway and wire it up. The order service remained untouched, closed for modification, while the payment system was open for extension. It was a game changer for agility and error reduction. The open-closed principle encourages a mindset of anticipating evolution. By embracing abstractions and polymorphism, we build systems that can grow and adapt gracefully, rather than collapsing under the weight of every new requirement. This flexibility is further supported by our next principle, the Liskov Substitution principle. Chapter 5, the L in Solid, Liskov Substitution Principle, LSP. Following the open-closed principle, we delve into the L of Solid, the Liskov Substitution Principle, LSP. This principle, named after Barbara Liskov, who introduced the concept of behavioral subtyping, ensures that inheritance hierarchies are correctly formed and behave predictably. The principle, objects in a program should be replaceable with instances of their subtypes without altering the correctness of that program. Barbara Liskov. In simpler terms, if you have a base class, like animal, and a derived class, like dog, you should be able to use a dog object wherever an animal object is expected, and the program should still work correctly without any unexpected behavior or errors. The derived class should not introduce any new preconditions, things that must be true before a method is called, or violate any existing postconditions, things that must be true after a method is called, defined by its base class. It also shouldn't change existing invariants, conditions that remain true throughout the object's life. Substitutability without surprises. Think about light bulbs. For decades, you've replaced an incandescent bulb with another incandescent bulb, and the light fixture functioned as expected. Later, LED bulbs were introduced. They look different internally, might consume less energy, and last longer. But importantly, you can screw an LED bulb into an incandescent light fixture, and it just works. The LED bulb is a subtype of light bulb, and it can substitute for the original incandescent bulb without breaking the fixture's functionality. The fixture doesn't suddenly need new wiring or a special adapter. It just works with the new bulb. Now imagine an energy-saving light bulb that, when screwed into a standard fixture, causes the fixture to explode, or only works if you clap your hands 3 times before flipping the switch. This new bulb cannot substitute for the original without altering the correctness or expected behavior of the fixture. It violates the light bulb substitution principle. In software, LSP ensures that when you build hierarchies using inheritance, the is a relationship, e.g., a dog is an animal, the subclasses truly are what they claim to be, behaviorally speaking. The square rectangle problem, a classic example, the most famous illustrative example of an LSP violation in software, is the square rectangle problem. Problem LSP violation. Let's say you have a rectangle class. Class rectangle, protected width, protected height, constructor width height, this width equals width, this height height, method set width, new width, this width equals new width, method set height, new height, this height new height, method calculate area. Return this width, this height. This seems perfectly normal. A rectangle has a width and a height, and you can change them independently. Now, consider a square. A square is a special type of rectangle where width is always equal to height. It intuitively feels like square should inherit from rectangle. Class square inherits from rectangle, constructor side. Super side, call rectangle's constructor. Method set width, new width. This width equals new width. This height, new width, also update height to maintain square property. Method set height, new height. This height, new height. This width equals new height, also update width to maintain square property. At first glance, this might look okay, but let's see how a square might be used as a rectangle. Suppose you have a function that calculates the area of any rectangle after resizing it. Function print area, rectangle, rectangle. Rectangle set width 5. Rectangle set height 10. Print area plus rectangle dot calculate area. If you pass a rectangle object to print area, you'd expect an area of 510 equals 50. My rectangle equals new rectangle, 2, 3. Print area my rectangle output, area, 50 expected. Now what happens if you pass a square object? My square equals new square, 4, initial width equals 4, height equals 4. Print area my square. Inside print area, when set width 5 is called on my square, its height also becomes 5. Then set height 10 is called, making its width also 10. So my square ends up with width equals 10 and height equals 10. The output will be 10, 10 equals 100. This is a violation of LSB. When my square, a subtype of rectangle, was substituted for my rectangle, the print area function expected to get an area of 50, but instead got 100. The behavior of the program changed in an unexpected way when a subtype was used. The square changed the existing postcondition of rectangle set width, W being that height would remain unchanged, or the invariant that width and height can be independently set. Solution, LSB compliant. The problem arises because the is-a relationship is misused. A square is not a rectangle in the behavioral sense if rectangle allows independent resizing of dimensions. They share some common attributes, dimensions, area, but their behaviors for modifying dimensions diverge. To fix this, rectangle and square should not have a direct inheritance relationship where square inherits from rectangle. Instead, they should both inherit from a common, more abstract base, or implement a common interface that doesn't make assumptions about independent dimension setting. Introduce an abstract base class or interface. iShape could be an abstract class or interface that defines common methods like calculate area, but not set width or set height. Interface iShape. Method calculate area, returns decimal. Independent implementations. Both rectangle and square would then implement iShape independently. Class rectangle implements iShape, width, height. Constructor, set width, set height. Calculate area. Class square implements iShape. Side, constructor, set side, specific to square. Calculate area. Now, a function expecting an iShape can compute its area, but it cannot assume it can independently set width and height because that behavior isn't part of the iShape contract. If another function needs to set dimensions, it would specifically ask for a rectangle or a square. This way, square doesn't break the assumptions of code written for rectangle. Benefits of LSB, robust inheritance hierarchies, ensures that your inheritance structures are sound and behave predictably, preventing hidden bugs caused by unexpected subtype behavior. Improved code reliability. Code that adheres to LSB is more robust because you can confidently substitute base types with their subtypes. Facilitates OCP. LSB is critical for the open-closed principle. If you depend on an abstraction, base class, or interface, in your OCP-compliant design, LSB ensures that any new concrete implementation you extend into the system will behave as expected and not break existing functionality. Enforces behavioral contracts. LSB emphasizes that not just the method signatures, but also the behavioral contract, preconditions, postconditions, invariants must be maintained across subtyping. Common pitfalls. Violating preconditions, postconditions. A subtype should not require more preconditions or deliver less postconditions than its parent. For example, if a mammal feed method requires food, dog feed, shouldn't also suddenly require a specific type of bowl. If mammal eat guarantees growth, dog eat shouldn't cause weight loss. Throwing unexpected exceptions. If a base method normally doesn't throw a certain type of exception, its subtype shouldn't suddenly start throwing it without proper handling. Modeling is a too literally. Just because A is a type of B in the real world doesn't mean it makes sense for it to inherit from B in a behavioral, substitutable sense in your software. The is a relationship in OOP should imply behavioral subtyping. An anecdote, the broken file processor. In a document processing system, we had a base document processor class with a method process file path. This method handled opening a file, reading its content, and performing some generic parsing. We then had specialized derived classes: PDF processor, text processor, image processor. One day, a new requirement came in to handle compressed zip file processors. A developer, trying to be clever, made zip file processor inherit from text processor, reasoning that a zip file could contain text. However, zip file processor's process file method, instead of reading line by line like text processor, unzipped the file into a temporary directory and then returned the path to one of the unzipped files. This looked fine in isolation. But then, a higher-level tool that iterated over a list of text processor objects and called process file path on each started failing when it encountered a zip file processor. It expected to get text content from process file directly, but instead, it got a temporary directory path. The zip file processor could not substitute for a text processor without altering the correctness of the calling program, which expected text, not a path. The fix was to recognize that a zip file processor was not a text processor in the LSB sense. The process file method for text processor needed to guarantee returning text content. We introduced a new abstraction, iFileUnpacker, and made zip file processor implement that, while text processor remained a specialized iDocumentReader interface. This allowed client code to correctly choose whether it needed to read text or unpack files, upholding LSB. The Liskov substitution principle is crucial for maintaining the integrity and predictability of your inheritance hierarchies. It forces you to think deeply about the behavioral contracts of your classes, leading to more robust and maintainable object-oriented designs. It works hand in hand with OCP, ensuring that your extensions truly extend, rather than unexpectedly altering, the system's behavior. Our next principle, the interface segregation principle, will focus on refining these contracts even further. Chapter 6, the I in Solid, Interface Segregation Principle, ISB. Having explored how the Liskov substitution principle helps define robust inheritance hierarchies, we now turn our attention to the I in Solid, the Interface Segregation Principle, ISB. This principle focuses on the design of interfaces and how clients interact with them. The principle, clients should not be forced to depend on interfaces they do not use. Robert C. Martin Uncle Bob. In essence, ISB advocates for creating small, highly focused interfaces rather than large, monolithic ones. If a class needs to implement an interface, it should only be required to implement methods that are genuinely relevant to its specific role. The Swiss Army knife problem revisited. Let's revisit our Swiss Army knife analogy, but from a different perspective. Imagine you're a person who just needs to stir your coffee. You are the client. If the only available stirring tool you can get your hands on is a Swiss Army knife, you now depend on an object that provides a knife, a screwdriver, a can opener, and a dozen other functions you don't need, just to get the stir function. You are forced to interact with, or at least acknowledge, a complex object. If the internal implementation of the can opener changes, even though you only use the stirring spoon, your tool might need to be recompiled or updated. This creates unnecessary dependencies. Consider instead that separate, smaller, specialized tools exist: a coffee spoon, a dedicated screwdriver, a dedicated knife. If you just need to stir, you pick up the coffee spoon. You depend only on the iStir interface and nothing else. If the design of the screwdriver changes, your spoon is unaffected. In software, using a single, fat interface, one with too many methods, can lead to classes implementing methods they don't actually need, and clients depending on aspects of the interface that are irrelevant to their use case. ISB in software, client-specific interfaces. ISB encourages us to break down large interfaces into smaller, more specific ones. Each client, the code that uses an interface, should only interact with the methods it actually needs. Let's consider a common scenario: a system for managing workers in a company. Problem: ISB violation. Imagine you have a single, large interface called iWorker that is meant to encompass all possible actions any type of worker might perform. Interface iWorker, method do work, method eat, method sleep, Method manage team, for managers. Method process orders, for order processors. Method take customer calls, for call center agents. Now, let's say you have different types of workers that need to implement this interface. Human worker can do work, eat, sleep, manage team, process orders, take customer calls. This worker can do everything, so it seems fine here. Robot worker can do work and process orders. But robots don't eat, sleep, manage team, or take customer calls. To implement iWorker, the robot worker would be forced to provide empty implementations or throw not supported exceptions for irrelevant methods. This violates ISB because robot worker is forced to depend on methods it doesn't use. This makes the robot worker class conceptually bloated and misleading. Its interface implies capabilities it doesn't have. Clients of iWorker are also affected. If you have code that iterates through a list of iWorker objects and tries to call eat, it would fail if a robot worker is in the list, even though eat is part of the iWorker interface. The client is forced to consider methods that are not universally applicable. Changes ripple unnecessarily. If the manage team method's signature changes, robot worker might need to be recompiled, even though it provides an empty implementation. Solution: ISB compliant. To adhere to ISB, we break down the iWorker interface into smaller, more granular, role-specific interfaces. Interface iWorkable. Method do work. Interface feedable. Method eat. Method sleep. Interface iManageable. Method manage team. Interface iOrder processor. Method process orders. Interface iCall taker. Method take customer calls. Now, each concrete worker class only implements the interfaces relevant to its capabilities. Human worker implements iWorkable, feedable, iManageable, iOrder processor, iCall taker. Still a lot, but this human can truly do all these things. Robot worker implements iWorkable and iOrder processor. Clean and concise, only implements what it can actually do. Clients wanting to assign a task now depend on the specific, small interface. A work scheduler would take a list of iWorkable objects and call do work on them. It doesn't need to know if they can eat or manage team. A feeding station would take a list of feedable objects and call eat and sleep on them. It wouldn't pass a robot worker to this station. This way, clients only depend on the minimum set of methods they need, creating a more flexible and robust system. Benefits of ISB: reduced coupling. Clients are less coupled to the details of other unrelated functionalities in the system. If an unused method's signature changes, it doesn't affect clients that don't use it. Increased cohesion. Interfaces become more cohesive, meaning their methods are closely related to a single, specific purpose. This makes them easier to understand and manage. Improved maintainability. Changes to parts of the system affect fewer clients, as clients only see the specific interface they depend on. Enhanced testability. Classes that implement smaller interfaces are easier to test because you only need to mock or provide implementations for the relevant methods. Better design. Encourages more thoughtful design of contracts and responsibilities. Common pitfalls: too many interfaces. Oversegregating can lead to an explosion of interfaces, making the system difficult to navigate. The balance is key. Interfaces should be segregated but still represent a meaningful, cohesive set of operations for a specific client role. Not applying to abstract classes. While commonly discussed with interfaces, ISB applies equally to abstract classes if they contain too many abstract methods that concrete subclasses don't all use. An anecdote: the overloaded iReport generator. At a previous company, we had a reporting module. Initially, there was a single iReport generator interface that had methods for everything: generate PDF report, export to CSV, print report, email report, archive report, generate Excel report. We had a sales reporter class that implemented this. It generated PDFs, CSVs, and Excel files, but then we introduced a compliance reporter class. This reporter only needed to generate PDF report and archive report. However, because it implemented iReport generator, it was forced to provide empty methods or not supported messages for export to CSV, print report, email report, and generate Excel report. This became problematic when a new developer was trying to add a feature to automatically email all generated reports. Their code looped through ListIReport generator and called email report. Suddenly, the compliance reporter started throwing errors because its email report was just an empty placeholder. The client, the new emailing feature, was hitting methods it shouldn't have been forced to depend on. The solution was to break iReport generator into IPT printable, IXF exportable, IXL exportable, a report emailer, a report archiver. Now, Sales Reporter correctly implemented all the relevant interfaces, and Compliance Reporter only implemented IPT printable and iReport archiver. The emailing feature now wisely operated on list iReport emailer, guaranteeing that every object in that list genuinely could be emailed. The system became cleaner, more focused, and much easier to extend predictably. The interface segregation principle guides us towards designing client-focused, finely grained interfaces. By doing so, we reduce unnecessary dependencies, improve modularity, and create systems that are easier to understand, maintain, and adapt. This principle often paves the way for the ultimate decoupling achieved by our final solid principle, dependency inversion. Chapter 7, the D in solid, dependency inversion principle DIP. We arrive at the final and arguably most powerful principle in solid, the dependency inversion principle DIP. This principle often brings together the benefits of all the preceding solid principles, enabling truly flexible and maintainable architectures. The principle: high-level modules should not depend on low-level modules. Both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. Robert C. Martin, Uncle Bob. Let's unpack this. High-level modules. These contain the application's core business logic and policies. They define what the system does, e.g., process an order, authenticate a user. Low-level modules. These contain the implementation details and utilities. They define how the system does things, e.g., connect to a database, send an HTTP request, save to a file. Traditional software design often sees high-level modules directly depending on low-level modules. For example, your order processor, high-level logic, might directly create and use a SQL database, low-level detail, to save orders. DIP flips this dependency on its head. It says that both high-level and low-level modules should depend on abstractions, interfaces, or abstract classes. These abstractions belong with the high-level module, or at least close to it, and define the contract that both sides must adhere to. The low-level module then implements this abstraction. The light switch analogy. Think about a standard electrical light system, high-level concern, the desire to turn a light on or off. This is the light switch concept. Low-level concern. The actual mechanism that produces light, e.g., an incandescent bulb, an LED bulb, a fluorescent tube. Without DIP, your light switch might be directly wired, dependent on a specific brand of incandescent bulb. If you want to use an LED bulb, you'd have to rewire or replace the entire switch. This is tight coupling. With DIP in action, the light switch, high level, doesn't directly depend on an incandescent bulb, low-level detail. Instead, the light switch depends on an abstraction, the iLightSource interface, which defines methods like turn on and turn off. The incandescent bulb, the LED bulb, and the fluorescent tube, low-level details, all implement the iLightSource interface. Crucially, the iLightSource abstraction itself doesn't depend on the specific bulbs. Rather, the bulbs depend on the iLightSource abstraction by implementing it. Now, you can plug any type of bulb, any detail implementing iLightSource, into the system, and the light switch will work correctly without needing modification. The high-level concern, switching light, is decoupled from the low-level concern, type of bulb. DIP in software. Inversion of control and dependency injection. In software, DIP is most commonly achieved through a technique called dependency injection, DI, which is a form of inversion of control, IOC. Instead of a high-level module creating its own low-level dependencies, those dependencies are injected into it from an external source, often a composer or assembler, part of the application. Let's revisit the concept of user authentication. Problem: DIP violation. Imagine a login service, high-level module, responsible for business logic, verifying credentials. It needs to check if a user exists in a database. Class login service. Method authenticate, username, password, direct dependency on a concrete database implementation. Database equals new MySQL database connection. Low-level detail. User record equals database fetch user, username. If user record and user record password equals password. Return true. Return false. This violates DIP because login service, high level, directly depends on my SQL database connection, low-level detail. If you later decide to switch to a NoSQL database or use a file system for user storage for testing purposes, you have to modify login service. It's not flexible. Testing login service in isolation is hard because it's always tied to a real database connection. Solution, DIP compliant, define an abstraction. Create an interface that represents the contract for storing and retrieving user information, regardless of how it's stored. This abstraction belongs logically with the high-level login service. Interface iUser repository. Abstraction. Method find by username, returns user record. Method save user, user record. Low-level modules implement the abstraction. Now, your specific database implementations, low-level details, will implement this iUser repository interface. Class MySQL user repository implements iUser repository. Detail. Logic to interact with a MySQL database. Method find by username, method save user, user record. Class MongoUser repository implements iUser repository. Another detail. Logic to interact with a MongoDB database. Method find by username, method save user, user record. Class in-memory user repository implements iUser repository. Detail for testing. Logic to store users in memory. Method find by username, method save user, user record. High-level module depends on abstraction. The login service now depends on the iUser repository interface, not a concrete implementation. The actual iUser repository instance is injected into the login service. Class login service, high-level module. Private user repository, iUser repository, depends on abstraction. Constructor repo, iUser repository. Dependency injection. This .user repository equals repo. Method authenticate, username, password. User record equals this .user repository find by username. If user record and user record password equals password. Return true. Return false. Now, the login service is entirely decoupled from the specifics of the database. You can inject MySQL user repository, MongoUser repository, or in-memory user repository at runtime, and the login service will work correctly without modification. This is the inversion of control and dependency. Instead of the login service controlling which database it uses, an external entity, the part of your application that creates login service objects, now controls and injects the dependency. Benefits of DIP. Decoupling. High-level policy is completely independent of low-level implementation details. This makes the system extremely flexible. Increased code reusability. Business logic in login service is reusable with any data storage mechanism. Enhanced testability. You can easily mock or stub interfaces for testing. When testing login service, you can inject a simple in-memory user repository instead of requiring a full database, making tests faster and more reliable. Improved maintainability. Changes to low-level details, e.g., switching database vendors, don't require changes to high-level business logic. Facilitates parallel development. Different teams can work on high-level logic and low-level implementations concurrently as long as they agree on the common abstractions. Common pitfalls. Forgetting to invert the owner of the abstraction interface should live logically with the high-level module, not the low-level one. Its purpose is to serve the high-level policy. Over-reliance on DI frameworks. While DI frameworks like Spring, Geist for Java, AutoFac, Unity for Net make managing dependencies easier, understanding manual DI is crucial. Don't use a hammer for every nail. Too many abstractions. Like with ISB, don't create unnecessary interfaces. Invert dependencies where volatility or variability is expected in the details. An anecdote, the untestable email sender. In a web application, There was a user service that, among other things, would send a welcome email after a new user registered. Inside the user service, the code directly created and used a concrete email sender class, class user service, method register user, user, save user to database. Email sender equals new concrete email sender, direct dependency. Email sender send welcome email user email. This immediately presented problems, untestable. To unit test register user, we always had to send a real email. This was slow, hit external services, and polluted mailboxes, making automated testing impractical. Inflexible. If we wanted to switch email providers, e.g. from SendGrid to Mailgun, we had to modify user service. Deployment issues. During development, if the email server wasn't configured, user service would break, even if the user registration logic was fine. The solution was a classic DIP application. We introduced an iEmail sender interface with a send email method. Concrete email sender then implemented this interface. Crucially, the user service then took an iEmail sender object in its constructor dependency injection. Interface iEmail sender. Method send email to address, subject, body. Class concrete email sender implements iEmail sender. Actual email sending logic. Class mock email sender implements iEmail sender. For testing, simply logs the email, doesn't send it. Method send email to address, subject, body. Print mock email sent to plus to address plus, with subject, plus subject. Class user service, private email sender, iEmail sender. Constructor sender, iEmail sender. This email sender equals sender. Method register user, user. Save user to database. This email sender send email, user email, welcome. Now for production, we injected concrete email sender. For unit tests, we injected mock email sender. The user service became completely testable and flexible, indifferent to the actual email sending mechanism. This inversion fundamentally changed our ability to test and adapt the system quickly. The dependency inversion principle closes out the solid principles by providing a powerful mechanism for decoupling components. By pushing dependencies towards abstractions and injecting concrete implementations, we create architectures that are supremely flexible, testable, and resilient to change. These 5 principles, when understood and applied thoughtfully, form the blueprint for building truly excellent object-oriented software. Now that we've explored each principle individually, let's see how they work together in practice, how to identify violations, and how to refactor your code to embrace solid design. Chapter 8, Solid in Practice, Putting It All Together. We've journeyed through each of the solid principles individually, understanding their distinct meanings, benefits, and how to apply them. While each principle stands strong on its own, their true power emerges when they are understood and applied as a cohesive set. They are not isolated rules, but rather a blueprint for creating robust, flexible, and maintainable software systems. How principles intersect. The solid principles are deeply interconnected and often reinforce each other. Adhering to one principle often makes it easier to follow another. SRP and OCP. A class with a single responsibility is inherently easier to be open for extension and closed for modification. If a class has multiple reasons to change, modifying one responsibility might break another, making it hard to extend without modification. When a class handles just one responsibility, you can safely extend its behavior, OCP, without worrying about affecting unrelated parts of its job. LSB and OCP. The Liskov Substitution principle is crucial for realizing the full benefits of the open-closed principle. When you extend a system by adding new concrete implementations that adhere to an existing abstraction, OCP, LSB ensures that these new implementations won't break the client code that depends on that abstraction. If your subclasses don't properly substitute for their base types, LSB violation, then your open for extension design becomes brittle and unpredictable. ISB and DIP. The interface segregation principle often helps in achieving dependency inversion. DIP advocates depending on abstractions, interfaces. If those interfaces are fat, ISB violation, then a high-level module might be forced to depend on a large interface, part of which the low-level implementation doesn't use, and part of which the high-level module doesn't interact with. By segregating interfaces, you create smaller, more focused abstractions upon which modules can depend, making the inversion of control much cleaner and more effective. DIP and all others. Dependency inversion is arguably the most impactful principle, as it provides the mechanism to achieve true decoupling. It often relies on well-defined interfaces, ISB, that respect behavioral contracts, LSB, and are part of components with clear responsibilities, SRP, enabling extensibility without modification, OCP. Without DIP, your well-structured, SRP-compliant classes might still be tightly coupled due to direct dependencies on concrete implementations. Think of it like building a house. SRP ensures each room has a clear purpose, kitchen for cooking, bedroom for sleeping. OCP means you can add a new room, extension, without tearing down existing walls, modification. LSB ensures that if you replace one type of window with another, it still fits and functions as a window. ISB ensures your light switch only controls the lights, not also the plumbing. DIP ensures your house wiring, high level, connects to a standard outlet, abstraction, not a specific brand of toaster, detail, so you can swap appliances freely. Each principle contributes to the overall stability, flexibility, and maintainability of the software architecture. Refactoring for solid. Identifying design smells. Applying solid principles isn't just for greenfield projects, new applications built from scratch. It's incredibly valuable for refactoring existing codebases. The first step in refactoring is often identifying design smells, symptoms in the code that indicate underlying problems and potential solid violations. Here are some common design smells and their corresponding solid principle violations. The God object, or large class. Smell. A class that does too much, is excessively long, and has many unrelated methods. Violation. Primarily SRP. Also likely contributes to violations of other principles by making the class difficult to extend, OCP, test, or substitute. Refactoring hint. Break it down into smaller, more focused classes, each with a single reason to change. Identify different roles or concerns within the large class. Shotgun surgery. Smell. A single change to a requirement necessitates modifications in many different, seemingly unrelated parts of the codebase. Violation. Often a symptom of SRP, responsibilities are scattered, or OCP. The system isn't open for extension, so existing code must be modified. Refactoring hint. Identify the missing abstraction or the scattered responsibility and consolidate it. Fragile base class. Rigidity. Smell. Modifying a base class causes unexpected breakage in its specialized subclasses or in client code that uses them. Violation. Primarily LSB, subtypes are not truly substitutable, or OCP. The base class is not closed for modification, so changes affect extensions. Refactoring hint. Reevaluate the is, a relationship using LSB. Introduce interfaces or abstract classes to define stable contracts without exposing too many implementation details. Feature envy. Smell. A method in one class seems to spend more time calling methods of another class than its own, indicating it might belong in that other class. Violation. Can hint at poor SRP, the method is in the wrong place, or inappropriate coupling. Refactoring hint. Move the method to the class it envies, or introduce a new class that encapsulates the logic performed across multiple entities. Rigidity, immobility, smell. The system is hard to change and hard to reuse in a different context. Violation. Often a violation of OCP, not open for extension, or DIP, tight coupling to concrete implementations. It can also stem from poor ISB, fat interfaces forcing clients to depend on too much. Refactoring hint. Introduce abstractions, interfaces, and use dependency injection to decouple modules. Identify areas where functionality could be extended without direct modification. Excessive branching. If-else if switch statements for types. Smell. Large if-else if or switch statements that decide behavior based on the type of an object or an enumeration. Violation. A classic sign of OCP violation. When a new type is added, this structure needs modification. may also signal an LSB violation if subtype behavior is managed by these external checks rather than polymorphic dispatch. Refactoring hint, replace with polymorphism. Define an interface abstract class and move the varying behavior into concrete implementations that adhere to that interface. Incremental improvement. You don't have to be perfect. It's important to understand that applying solid principles is not about achieving perfection from day one. It's an ongoing process of continuous improvement. Start small. Don't try to refactor an entire monolithic application to be perfectly solid overnight. Pick a small, manageable part of the system that causes frequent headaches or is undergoing new development. One principle at a time or two. Focus on applying one or two principles at a time. For instance, start by ensuring classes have a single reason to change, SRP. This will naturally make it easier to apply OCP later. Then, think about decoupling dependencies with DIP. Tests are your safety net. If you're refactoring existing code, ensure you have automated tests, especially unit tests and integration tests, in place. These tests will immediately tell you if your refactoring introduced a regression. Without tests, refactoring is like fixing an airplane mid-flight without knowing if your tools are breaking critical components. Code reviews. Discussing design decisions with peers during code reviews is invaluable. Other developers can spot design smells you missed or suggest alternative ways to apply solid principles. Pragmatism over dogmatism. Solid principles are guidelines, not rigid laws. There might be situations where a strict adherence yields overengineering for a simple problem. Use judgment. If a simple if-else is clearly more readable, and the logic is truly stable with no foreseeable extensions, don't create an entire strategy pattern just to hit OCP. The goal is maintainable software, not architectural purity for its own sake. An anecdote: the legacy reporting system's transformation. I once worked on a legacy financial reporting system. It was infamous for bugs and being incredibly slow to change. Adding a new report or modifying an existing one could take weeks. The core of the problem lay in a massive report generator class that violated nearly every solid principle. It parsed different data sources, applied business rules, formatted output, PDF, Excel, CSV, and emailed reports, all within one or two sprawling methods. Our initial attempt at refactoring was daunting. It felt like trying to defuse a bomb blindfolded. But we started small. Applied SRP. We first identified that printing, emailing, and archiving were distinct responsibilities from generating the report data. We extracted report printer, email sender, and report archiver classes. Applied OCP. The report generator was filled with if statements for different report types and output formats. We introduced an iReport format interface and iReport type interface. Now, adding a new report format, e.g., HTML, meant adding a new class implementing iReport format, not touching the report generator. Applied DIP. The actual data access layer was hard-coded within the report generator. We refactored it to depend on an iReport data source interface, so we could inject different data sources, database, API, static file, without changing the core generator. The process took time, but the transformation was dramatic. What was once a no-go area for new features became manageable. Adding a new financial report that needed specific formatting and data pulled from a new API went from weeks to days. Bugs became easier to pinpoint. The system, once rigid and immobile, became adaptable and a foundation for future innovation. It was a powerful demonstration that even the oldest, most tangled code can benefit from solid principles incrementally. These principles are indeed a blueprint, not a magic fix for everything. They guide you towards writing modular, flexible, and robust code. Understanding how they interact and how to identify their violations in your codebase is the first step towards building software that truly stands the test of time. Before we conclude, let's briefly touch upon some other complementary design principles and patterns that often work in harmony with Solid. Chapter 9: Beyond Solid. Complementary principles and patterns. The Solid principles provide an excellent framework for designing maintainable and flexible object-oriented software. However, they are part of a broader landscape of software design wisdom. Many other principles and established design patterns complement Solid, helping you build even better systems. Other important design principles. While Solid focuses on achieving robust, object-oriented structures, other principles address different aspects of software development. Dry, don't repeat yourself. Meaning, every piece of knowledge in a system should have a single, unambiguous, authoritative representation. Impact avoids redundant code, which makes systems harder to maintain. A change in one place requires changes in many and more prone to inconsistencies and bugs. If you find yourself copying and pasting code or writing the same logic in multiple places, you are likely violating Dry. How it relates to Solid. Dry and SRP often go hand in hand. By giving a single responsibility to a class, you make that logic reusable, thus avoiding duplication. OCP encourages extending with new code rather than modifying existing, which can also reduce duplication of underlying logic. YAGNI, you ain't gonna need it. Meaning, don't add functionality until you actually need it. Impact promotes simplicity and avoids over-engineering. Building features prematurely based on speculative future needs often leads to wasted effort, increased complexity, and irrelevant code that requires maintenance. How it relates to Solid. While Solid encourages anticipating change and extension, especially OCP, YAGNI acts as a counterbalance. Don't build elaborate abstraction hierarchies or complex extension points just because it might be needed someday if there's no concrete, near-term requirement. Balance the effort of designing for flexibility with the immediate needs of the project. KISS, keep it simple, stupid. Meaning, most systems work best if they are kept simple rather than made complicated. Therefore, simplicity should be a key goal in design, and unnecessary complexity should be avoided. Impact promotes clear, understandable, and manageable code. Complex code is harder to debug, test, and maintain. How it relates to Solid. Solid principles, when applied correctly, often lead to simpler, more focused components. For example, SRP leads to smaller, easier-to-understand classes. DIP makes dependencies explicit, which can simplify component interaction. However, misapplying Solid principles, e.g., over-engineering an abstraction where a simple conditional would suffice, can lead to unnecessary complexity, violating KISS. Introduction to design patterns. Design patterns are documented, reusable solutions to common problems in software design. They are not concrete classes or libraries, but rather descriptions or templates for how to solve problems in various contexts. Many design patterns are direct applications of the Solid principles. Understanding common patterns can help you apply Solid effectively in real-world scenarios. Here are a few prominent examples. Strategy pattern manifests OCP and DIP. Problem: you have a family of algorithms and you want to use them interchangeably. Solution: define an interface, the strategy, for the algorithms, and then encapsulate each algorithm in a separate class that implements that interface. The client class depends on the interface, not the concrete algorithm. Solid connection. This is a perfect example of OCP, open for new strategies, closed for modifying the client code, and DIP. Client depends on the strategy interface, not a concrete strategy implementation. It also often leverages ISB by having a clear, focused strategy interface. Factory method pattern abstract factory pattern manifests OCP and DIP. Problem: you need to create objects without specifying the exact class of object that will be created, allowing subclasses to decide which class to instantiate. Solution: define an interface for creating an object, but let subclasses or client code decide which specific concrete class to instantiate and return. Solid connection enables OCP by allowing new product types to be added without modifying existing client code that requests products. It achieves this by depending on an abstract factory creator, DIP, rather than concrete product classes. Observer pattern manifests OCP. Problem: an object, the subject, needs to notify other objects, the observers, when its state changes without knowing the specific classes of those observers. Solution: define an interface for observers. Subjects maintain a list of observers and notify them through this interface. Solid connection. The subject is closed for modification in terms of who it notifies. If a new type of observer wants to be notified, it simply implements the observer interface and registers itself. The subject is open for extension with new observer types. The important takeaway here is not to memorize all patterns, but to recognize that they provide established ways to apply solid principles to common design challenges. When you encounter a pattern, try to identify which solid principles it embodies and how. The role of testing in good design. It's difficult to discuss good software design without emphasizing the critical role of testing, particularly automated unit testing. Tests guide design. Writing unit tests forces you to think about how your classes and methods interact. If a class is difficult to test in isolation, it's often a strong indicator of a design flaw, perhaps a violation of SRP. Too many responsibilities make it hard to mock dependencies, or DIP, tight coupling to concrete classes, prevents easy mocking. Tests validate design. Automated tests provide a safety net. When you refactor your code to apply solid principles, tests immediately alert you if you've broken existing functionality. This confidence allows you to make larger, more beneficial design changes. Solid promotes testability. Classes adhering to SRP are easier to test because they have a single, well-defined purpose. OCP and DIP allow you to inject mock or stub versions of dependencies, meaning you can test components in isolation without involving complex external systems like databases or web services. ISB ensures that the interfaces you're mocking are small and focused, simplifying test setup. In summary, while solid principles provide the intellectual framework for building well-structured object-oriented software, other principles like DRY, YAGNI, and KISS ensure it's also concise, timely, and simple. Design patterns offer proven solutions that effectively embody solid principles. And finally, automated testing is the indispensable practice that validates your design decisions and provides the confidence to evolve your codebase. With these broader considerations in mind, you are now equipped with a powerful toolkit for crafting exceptional software. The final chapter will summarize your journey and offer practical steps for continued growth. Chapter 10. Your journey to better design. We've reached the end of our exploration of the solid principles. From unmasking the God object with the single responsibility principle to decoupling with dependency inversion, you now possess a powerful framework for building software that isn't just functional, but truly resilient, adaptable, and a pleasure to work with. Recap of key takeaways. Let's quickly revisit the core message of each principle. Single responsibility principle, SRP. Your classes should have only one reason to change. This means assigning them a single, well-defined responsibility, leading to more focused, maintainable, and testable components. Think specialized tools, not a cluttered supertool. Open-closed principle, OCP. Your software entities should be open for extension, but closed for modification. Achieve this by depending on stable abstractions, interfaces, or abstract classes, allowing you to add new behaviors by writing new code rather than altering existing, tested code. Think plug-and-play, not rewiring. Liskov Substitution principle, LSB. Subtypes should be substitutable for their base types without altering correctness. If you use a subclass where a base class is expected, the program's behavior should remain predictable and consistent. Think of a light fixture that works perfectly with any compatible bulb, old or new. Interface segregation principle, ISB. Clients should not be forced to depend on interfaces they do not use. Favor small, specific, client-focused interfaces over large, bloated ones. Think of giving someone only the specific tool they need, not a whole toolbox. Dependency Inversion principle, DIP. Depend on abstractions, not concretions. Both high-level modules, business logic, and low-level modules, implementation details, should rely on interfaces, reducing tight coupling and promoting flexibility and testability. Think of a universal, remote controlling devices through a standard interface. Together, these principles are not just theoretical constructs. They are practical guidelines forged from decades of experience in the software trenches. They tackle the fundamental challenges of complexity, change, and collaboration that define software development. Tips for learning and practicing. Understanding these principles intellectually is the first step. Applying them effectively in your daily coding is the journey. Here's how you can continue to learn and practice. Code reviews with a solid lens. Participate actively in code reviews, both giving and receiving feedback. When reviewing, ask yourself, does this class have too many responsibilities? SRP. If a new type of something is introduced, will this code need to be modified? Or can it be extended? OCP. If I swap out this implementation with another one from the same family, does everything still work as expected? LSB. Does this interface force its implementers to bring along methods they don't actually use? ISB. Are high-level business rules depending directly on low-level details? DIP. Refactor legacy code. Find a small, troublesome part of an existing code base and try to refactor it using one or two solid principles. Start with SRP, as it often clears the path for others. Use automated tests as your safety net. Practice on small projects katas. Begin new personal projects or coding challenges with solid principles in mind from the beginning. Even small exercises like building a simple calculator, a shape drawing program, or a basic e-commerce cart can provide opportunities to apply these concepts. Read and analyze open source code. Explore well-known open source projects. Try to identify how they apply, or sometimes don't apply, solid principles. Learning from real-world examples, both good and bad, is invaluable. Seek mentorship. If you have experienced software architects or senior developers around you, ask them about their design decisions. Discuss your thoughts and ask for feedback on your design approaches. Teach others. The best way to solidify your own understanding is to explain these concepts to someone else. Try articulating why a particular design choice adheres or violates a principle. The importance of continuous learning. The landscape of software development is constantly evolving. New languages, frameworks, and paradigms emerge regularly. However, principles like SOLID are timeless. They address fundamental problems of software design that transcend specific technologies. They are the bedrock upon which you can build adaptable skills for the future. Embrace a mindset of continuous learning. Read other books, follow influential software architects, and engage with developer communities. The more you immerse yourself in discussions about design, the more intuitive these principles will become. Recommended further reading and resources. To deepen your understanding and explore related topics, consider the following: books by Robert C. Martin, Uncle Bob, Clean Code, a handbook of agile software craftsmanship. While not solely about SOLID, it extensively covers principles of good code hygiene and design. Clean Architecture, a craftsman's guide to software structure and design. This book delves deeper into how SOLID principles underpin broader architectural decisions. Patterns of Enterprise Application Architecture by Martin Fowler explores many common design patterns and their application in enterprise systems. Design Patterns, Elements of Reusable Object-Oriented Software by Erich Gamma et al. The Gang of Four book, the classic reference for design patterns. Online resources. Many excellent articles, blogs, and video courses are available from experienced practitioners that discuss SOLID and related design topics. Look for reputable sources and community forums. Your journey to becoming a skilled software designer is a marathon, not a sprint. There will be times when you struggle to apply these principles perfectly, or when you choose to deviate for pragmatic reasons. That's perfectly normal. The goal is not perfection, but continuous improvement and a deeper understanding of how to build software that serves its purpose effectively, now and in the future. May your designs be clean, your code be flexible, and your systems be solid. Happy coding!